In the first part of this video, we discovered that the energy of a photon of a yellow light photon from this lamp had 3.42 times 10 to the negative 19 joules. The energy of the wave, of a single wave from that light. We're now going to be tasked with determining if that would be higher or lower for orange light and then blue light. We're looking at the energy and the frequency. So this is more qualitative than quantitative. We learned in the last video that the wavelength of this light in meters, which is useful to us, is 5.82 times 10 to the negative 7th meters. According to Roy G. Biv, which would be useful for you to memorize, Roy G. Biv is the part of the visible spectrum that we can see, visible light, Roy G. Biv, which tells us that it's going to go from longest wavelength to shortest wavelength. So red light has longer wavelengths, and this is not to scale. I'll do that a little bit more dramatically. Red light has longer wavelengths, violet light has really short wavelengths, and then in between is the in between. It just gets shorter as you go in that direction. So let's look at our equations and see how direct versus inverse proportions work for these equations. Energy is equal to Planck's constant times frequency, and the speed of light is equal to wavelength times frequency. I'm going to rewrite this in a way that may be a little more useful, or just as a refresher of how you can rearrange these equations. Frequency of light is equal to the speed of light divided by lambda. And then once more, I will combine these two equations, as you've already learned how to do, into an equation that will help us understand how energy and wavelength relate more clearly, and that is E equals h times c divided by lambda, which is the wavelength. So these are three equations that are highly related to each other. We're asked, how would the energy and the frequency of this yellow light, this yellow photon, compare to the wave or the photon energy and frequency of orange light? So yellow versus orange. Yellow would be here, and it has shorter wavelengths than orange because orange is closer to red. So look at this equation first. For this first piece, we're going to look at the energy comparison. Because the wavelength of orange light is longer than the wavelength of yellow light, so we have a larger denominator. Because the wavelength of orange light is longer or larger than yellow light, it would actually have less energy. So if you think about this, energy equals, because Hc is a constant, I'm just going to call that 1. The energy of, actually I'm going to go back and do this a little bit different. The energy of orange light, so I'm going to put O-R-A-N-G-E, would be equal to a constant, which is h times c. That's because that's just what they are. They are not going to change regardless of the color or energy of a wave, divided by a high number. Let's just say that the orange light wavelength is a 3. It is not 3, and that's not even doesn't have any units for us. But we know that orange light has a longer wavelength than yellow light. So if we say that the wavelength, which is lambda, so it would be this. If we say the wavelength of orange light is 3, we were to compare that to the wavelength of yellow light, which is shorter than the wavelength of orange light according to this, we would just give it any old constant number, so we know, or any number. We know that Hc is a constant, so we're just going to call it 1 just for comparative purposes. 1 over 3. If 3 is a wavelength for orange light, then the yellow length wavelength should be shorter than that. So we're going to give it a 2. You may not be able to see that. It's a 2. If we're comparing the wavelengths, we know that yellow light would have a shorter wavelength. What's the overall value of 1/3 versus 1/2, which would be equivalent to the energy? Because of the shorter wavelength of yellow light, it has more energy. You know that 1/2 is a larger number than 1/3. So it's called an inverse relationship. So I will write this again. Energy equals hc over lambda, which tells us that energy is inversely proportional to, so inversely proportional to the wavelength, which is, of course, lambda. So as a reminder of what inversely proportional to means, that means that as the value of one goes up, the other one goes down. So as orange light and increasing from the red to the yellow, or from the red to the violet direction, as the wavelength goes down, the amount of energy goes up, and vice versa. As the wavelength goes up, the amount of energy goes down. So because red, the red end of the spectrum, has a longer wavelength, it actually has less energy because of the equation. The equation verifies that. And the violet end of the spectrum has a shorter wavelength and more energy. So orange light would have lower energy. So orange is lower energy because of the longer wavelength, so it's inversely proportional. We can actually answer the blue part of the question now. This says blue light. It's asking us about blue light and how the energy relates. So using the same logic, because blue light has a shorter wavelength than yellow light, it would have more energy. So blue light would have higher energy than the yellow light because it has a shorter wavelength. You can probably look at the equation immediately and determine how we'd answer the second part of these dual questions. And now we're going to look at the frequency. So this is how energy is related. How is frequency related now? This is called a direct proportion because as the frequency of light goes up, and h is just a constant, the energy of the light will also go up. So orange light would have a lower frequency, and because it has a lower frequency, it has a lower energy. So I'm going to put lower F leads to lower E. So the lower frequency of orange light leads to a lower energy because as F would decrease, so would E, and as F would increase, so would E. And blue light would follow that same logic. Blue light, because it has a higher frequency, because it's closer to the violet end, the higher frequency leads to the higher energy. And that would be how you would qualitatively compare them. Notice how we were not given wavelengths of either blue or orange light, but we could determine the differences in energy and frequency, relative differences in energy and frequency versus yellow or any other color based on these equations and our understanding of direct versus inverse proportions. Inverse proportions are graphed like this with your two variables on the x and the y. So as one goes up, the other goes down. And direct proportions, such as the frequency-energy relationship, would look like this, which is as one goes up, the other also goes up. Or as one goes down, the other also goes down.